Hello guys, welcome to the final video of this lecture of this project series, project tutorial. Now the next task that we're going to perform is basically, as discussed in the last video, that we are going to prepare the tokenizer. So a tokenizer builds the vocabulary and converts a word sequence to an integer sequence. So let's just go ahead and build tokenizer for the text and summary. So in order to create the text tokenizer, we need to import from Keras library because we are using Keras. So we'll just do preprocessing.text. We'll just import tokenizer, and again we need keras.preprocessing.sequence import pad underscore sequences. We already did this step before, so we do not want to repeat the step. So what we can do is directly take tokenizer and instantiate with the tokenizer. Okay, I just wrote it. Now for the X tokenizer, we want to fit the data. So fit on text list, and the X training set. We only want to train the test set. Now just let's run this piece of code. Now let's run it. Okay, so now it's done. Now what we have to do is we will be just look for the rare words as its coverage. So now let us look at the proportion of rare words and its total coverage in the entire text. So here I am defining the threshold to be 4, which means word whose count is below 4 is considered as a rare word. So for this, we just need to find thresh equals to 4. Again count 0 dot underscore count, that will take a random value. Again for frequency, determine the frequency, we'll just take frequency also zeros, and for dot underscore frequency, how many times it appeared to again to be 0. Now I'll use a for loop. So for key comma value in X underscore tokenizer dot word underscore counts dot items that we're dealing with, dot underscore cnt equals to dot underscore cnt plus 1. Now if this goes for same, so dot underscore frequency should be equals to dot underscore frequency plus 1. Now finally frequency equals to frequency plus value. Now finally what we're going to do is print the percentage of rare words in vocabulary just with the value cnt divided by dot underscore cnt, and for percentage marks we multiply it with 100. And same statement we'll do it for the value, so I'll just copy and paste it as a above statement. Okay, now just press enter. So here the function is very proud, and you can see the percentage of rare words in vocabulary is around 66%, and total coverage of rare words is about 2.953%. So what you need to remember is like the dot underscore cnt that you just defined gives the size of the vocabulary, which means every unique words in the text. Cnt just give me the number of rare words whose count falls below the threshold. The threshold we set is to 4. So it just return the words which falls before the threshold, that is 4. And dot underscore cnt minus cnt, if I do dot underscore cnt minus cnt will give me the topmost common words. So now let us define the tokenizer with the topmost common words for refuse. So for that we just need to do X underscore tokenizer equals to capital tokenizer, and inside it num underscore words should be equals to dot underscore cnt minus cnt that we just talked. Rex underscore tokenizer dot fit, because we want to fit our data set. So fit underscore on underscore text, the value of list that we want to deal with. So x underscore tr, because we are just training. Now we need to convert text sequences into integer sequences. So for that, we'll just take a scene value, and we just need to take the tokenizer dot text underscore to underscore sequences, the function, and we just pass on the training set. And for validation, again, we just do the same thing. Sequence will be equals to x underscore tokenizer dot txt underscore to underscore sequences. Wait, the function we're about to get x underscore for the validation set. Okay, we just did correct now. Okay. Now we need to pad 0 up to the maximum length, because we also need padding, because we need to replace the values of what if the values are not up to the maximum length. So we will just substitute those values with the 0. So for that, we just do x tr equals to pad underscore sequences. And we just need to pass x underscore tr underscore sec, and we just pass max length that we want to have. We should be equals to max underscore length, and we also want to define the padding. So we'll have padding equals to post, because this post kind of padding we need. Okay, now same will be done for x underscore val, same pad underscore sequences. Okay, you can even see what this pad sequences give. You can just check on the value what each function is doing. So for validation, we'll just do, instead of writing, let me just copy paste it. And after that, we just want to copy paste it. Okay, I have even pasted the indentation, like I have also commented like which function and at what level we are performing what thing. So you can see it, see here. So now at last we want to have the size of the vocabulary, so we can just have the tokenizer numwords +1. Now we just run this sentence, this piece of code. So it will take sort of time. Now we just pass on the value of, in order to find the value of the x4. And yeah, comes out to be 8440. Now we'll prepare a tokenizer for reviews on training data. So for that, we just need to again do tokenizer equals to tokenizer x type y underscore tokenizer dot fit underscore on underscore txtx, and we just need to pass the training set, this y underscore training for the label set. Now when I run this piece of code, it will just, even though, okay, it says MD has no attribute lower. Okay, so in order to deal with this, okay, so basically that error was just an error due to runtime. So I just clicked runtime and I restart and run all. So it basically cleared my error. Okay, now let's back to it. Now let us look at the proportion of rare words and its total coverage in the entire summary. So here I'm defining the threshold to be 6, which means words whose count is below 6 is considered as a rare word. So we will even follow the same steps that we defined here. Threshold equals to 4, and again this value to be 0, and we'll just reiterate the same process over the following. So what I'll do is just simply directly paste the entire code. Now you can see here. So this is the entire piece of code. Now when I shift plus enter and just threshold to be 6. Now you can see that the percentage of rare words in vocabulary is around 78% and total coverage of rare words is around 5.39%. So now let us define the tokenizer with the topmost common words for summary. Again, we will use this particular process that we just used for the training sets, and we'll just have the same values and we'll just replace it with the Y tokenizer. So again, let me just copy and paste the code. So I'm just taking the code and it's just fitting the data set. Okay, now it has to. Now let us check whether the word count of the starts token is equal to the length of the training data. So for that, we just want to do tokenizer dot word underscore counts, and we'll just need to specify that SOSTOK value with the length of Y underscore TR. On a press shift press enter so you can see. So now here I will be deleting the rows that contain only start and end tokens. So in order to delete that, I have to just take again empty dictionary, and I'll use for I in range, I will use length and Y underscore TR. I'll just take a value CNT variable and assign the value, initialize it to 0 value. Now I'll again run a loop inside this loop for the TR values, for the I values again, and I have to mention that if J is not equal to 0, then if it is not, then I'll just increment this value with the +1, and I have to specify if CNT double equals to 2, int dot append the value I. Now finally I just need to replace the value tr equals to delete the value. So in order to delete, I'll just pass on the value y underscore tr, and I want to delete the row, so access equals to 0, and then if I want to delete via the column, I'll specify access equals to 1 equals to np dot delete. Okay, I forgot to mention np dot delete here. Dot delete. Now again x underscore tr comma d comma access equals to 0. Forgot to pass on int here. Now we to go. Now when I run this, okay, the process is done. I'll do the entire process for the validation test also. I'll just copy and paste the code for the validation set. Press shift plus enter. Now finally, our final step is to build the model. So we are final at the model building part. So but before we do that, we need to familiarize ourselves with a few terms which are required prior to building the model, and let me just copy paste it here. So I'm just copy pasting it here, shift plus enter. Okay, now first thing that you need to remember is return sequences when set to true. So when the return sequences parameter is set to true, LSTM produces the hidden state and cell state for every time state. When return state equals to 2, so LSTM will produce the hidden state and cell state for the last time step only. And initial state is basically, this is used to initialize the internal states of the LSTM for the first time step. And finally, the stacked LSTM. Stacked LSTM has multiple layers of LSTM stacked on top of the each other. So this will automatically give us the best representation of the sequence. This is how we are able to see the representation more in a best and more better representation. And I even encourage you to experiment with the multiple layers of LSTM stacked on top of the each layer. So it's a great way to learn this. Okay, so now here, and the one more thing is like here we are building a 3-stack LSTM for the encoder. So now let's code for the encoder. Now if I write the code, it will take some time. So I will directly copy paste the entire code, and I'll just make you understand what each step is doing. So as now you can see, this is the entire code. So I've divided the 3-stack layer. So the first I've just imported KRS import backend as K, because I won't be using KRS every time, so I need to just make it short now. So I just took a short variable KRS as K. Now first of all I have to clear that any running sessions I need to stop it. So I will just clear the sessions by using this particular clear underscore session, which will just clear any running session. It will just get cleared. Now these are the latem dim and embedding dimensions. These are the dimensions that we need to make care of while dealing with the model, when we are dealing with the model. So I've just taken 300 and 100. That means 300 rows and 100 columns I would be taking as the embedding dimension. And the encoder inputs. For encoder inputs, you need to just input the shape. So for shape also, the dataset shape that I will be inputting will be just have contained the max test length, as we know that we have just found out this value with the power piece of code. And for embedding layer, you can see the function, the trainable has been set to true. And for the first layer of the encoder of LSTM, we have just taken these particular values. You can just take this piece of code. Dropout has been set to 0. For layer 2, the process has been done same, and for the layer 3 also. Now the encoder state has been done. Now it's time for the writing the decoder step. So in order for the decoder step, we have done for the following. So you can see input have shape has been taken as none for the TSC library, and perhaps you might be familiar with these particular concepts. So again, at the final thing, I've taken the attention layer as well and decoded with the LSTM output. So for that, I have decoded, and I've mentioned the axis equals to -1 because I want to take the every row and every column into the consideration. That's why I have taken it, and I've named this a concat. And softmax activation function have been taken because softmax activation function is basically used for classification purposes. So for classification purposes, as you know, we use softmax activation function, which is just equals to 1/1 plus a to the power -x. So now this is the function that we'll be using for. So after running this piece of code, we get the following output. Now you can see each layer has been shown here with the respective output and the shapes. Like these are the outputs and the shapes of the data set. At what layer, what was the dimension of that data set has been also labeled here. The number of parameters has been used, connected to these are the shapes, and this is the final result we got. Now the next step is basically for sparse categorical variable. So I am using sparse categorical cross entropy as the loss function, since it converts the integer sequence to one hot vector on the fly. So this overcomes any memory issues. So for that, we just need to do model dot compile, and you need to specify optimizer as RMS prop, followed by loss. You want to sparse because we are using. You can even use your one if you want to use. Pretty cool. Wait, let me just paste the code. Now after this, if I run just the loss I've taken is the sparse categorical cross entropy. Now I've run this statement. Now after this, remember the concept of early stopping that we just discussed. So it is basically used to stop the training the neural network at the right time by monitoring a user specified metric. So here I'm monitoring the validation loss. So our model will stop training once the validation loss increases. So for that again, we need to paste the code. So for that particular, the code will be like this, using the early stopping. And for monitoring, as we have discussed, that we'll be using for the validation loss. That's why I have wrote val underscore loss. Now after this, let's just run the code. Now after that, we will train the model on the batch of size of 128 and validate it on the holdout set, which is the 10% of the data set. So for that, we just need to write history equals to model.fit and pass on the datasets values. So let me just write the code. After pasting the code, we'll just run the code. So as you can see, the first epoch is run. We will run it for 50, and the batch size I told you about 128, but we'll take 512. so that I can make the training faster. So I just took 512. Okay, what if I just stop it right now, and for the instead of I just give 120. Let's check, will the training be faster? Now let's just wait till the data gets, till this line gets run. Now I'm just pausing the video. Let's just wait for the result. Now, since the training time was taking very much a long time, only for these two epochs it took about more than 20-25 minutes. That's why I just stopped it on the second epoch. Now, for understanding the concept, let's just stop at the 22 epochs. But if you want, you can even stop it with the 50 or 30 epochs. I would suggest like at least take 10 epochs. Now, next thing that we want to look is understanding the diagnostic plot. And now we'll plot a few diagnostic plots to understand the behavior of the model over time. So for that, again, we will be going to use Matplotlib. So without typing the code, I'm just going to paste it so that we can just go on faster. I've just pasted it. Now, since for the two epochs, you can see the training and test error. Only for the two epochs, you can see the train error is from the plot. You can see that the validation scores has been increased from the second on for more like 0.5 epoch to the successful epochs, and the training is stopped at the one epoch. It will even go if we just continue the test. So if you want to visualize this graph even further, for that you have to use more number of epochs here so that the graph will even have a curvature like thing. Now let's set up the inference for the encoder and decoder. Again, I am just copying the code. Now you can see that this piece of code what does. So first we'll just encode the input sequence to get the feature vector. So in order to get it, just you have to use the model that we just imported, and you have to provide input as the encoder inputs, and outputs you need to provide that encoder outputs, and you need to provide states, and you need to provide the state C. Then you have to do the decoder steps. So below tenses will roll the states of the previous timestamp. So for that you have to use this piece of code. If you want to get the embeddings of the decoder sequence, that you need to just use the DAC EMB layer, and you need to pass on the decoder inputs that you calculated from above. And for attention inference, you have to follow the same exact step. Now this entire process can be implemented in a function. So you can, again, I'm going to paste code for the decode sequence and tense, so which you can use it in order to decode this. You just need to like input the sequence, and it will just decode your sequence, and it will generate you the function that you require. So you can just take a sample token and you will. Now when I run this particular piece of statement, so it's now let us define the functions to convert an integer sequence to a word sequence. So for that, again, I'm going to define some particular functions that you can just copy and paste it, like just see. Now basically this function, what it does is like it will take any input sequence and it will just convert your word sequence into an integer sequence so that it can be mapped correctly. So you just need to run space shift plus enter. After this function is done, now you have the few summaries generated. Now if you want to see the future summaries that will generate from the data you have trained the model, so you just need to type here, and for in range, like you can just run this. Now you can see summaries are getting generated. Okay, so even the reviews are getting as an output. Now let's just take anything. So the review was strong, much flavor, little aroma, tried, purchase, another time, simpler failure. So out of that, the summary has been given as great. Again, the grade. This is the summary which has been taken from the entire data set. If you would have used the more the number of epochs, the more number of letters and words have been outputted here. So the good amount of summary would have been generated. Just because we have used only for 2 epochs, the result are showing like this. But if you would have taken more number of epochs in the training, then you would have gotten like more words in the summarized manner. So that's how you would have compared it, the result. So finally we got the results for the 100 summary, and this is how we generated summary for our entire review data set. So finally, this is how you generate summary for the words. So it is quite a hectic task, and it is perhaps a little bit complex, but you can even apply this project by yourself, and it will, by doing it, you will feel more attached and you will have a clear picture of it. So this is really cool stuff. Even though the actual summary and the summary generated by our model do not match in terms of words, both of them are conveying the same meaning. Our model is able to generate a legible summary based on the context within the text. So this is how we can perform text summarization using deep learning concepts in Python. Now, one more thing that we need to keep in mind is, the one important thing that is like you can even improve the performance. So this was just a generalized model. So if you see one of the review, so it says like that gives open last long thing, and the summary we got was great. So if you would have trained your model for more number of epochs, you would have got great number of results. And the one more thing is like how you can even enhance the performance of your model. So you can even enhance the performance of models by just like I would recommend you to increasing the training data set. So that will like build the model by increasing the data set. We just took around 100,000 samples. You can take more number of samples and you can build the model. The generalization capability of a deep learning model enhances with an increase in the training data set. Another thing that you can do, we just use one directional. You can even use bidirectional STM, which is capable of capturing the context from both the directions and result in a better context vector. And you can even use the beam search strategy for decoding the text sequence instead of using the greedy approach, which is argmax. And you can finally evaluate the performance of your model based on the BLEU score. And finally, you can implement the pointer generator networks and coverage mechanism. So this was much about the text summarizer. So hope you would have enjoyed the video. I know it is a bit complex, but don't worry. If you perform this project, you will get to have a clear picture about it. Thank you so much, guys, for having me there. And yeah, that's it. Thank you.